In the eastern Massachusetts town of Weymouth, three odd features are found in the landscape. First, there is a massive rock, appropriately called Big House Rock. How in the world did this huge, house-sized boulder get here? Was it dropped here by giants? A few miles away, snaking along a tidal estuary, is a long, narrow hill. A first-time visitor might ask, could such a steep, long, narrow hill be a natural feature? And near that hill is another hill, but this one seems perfectly rounded, unlike the long hill to its south. It might just be an ordinary hill, but could its round shape hold a secret? What could these three odd geologic features have in common? A huge boulder, a long, narrow, winding hill, and a perfectly round hill. It turns out that these seemingly unconnected features are also connected in an even more surprising way to events occurring way up in the Arctic. Because when you study Arctic glacier systems, you begin to learn that features like those in Weymouth were also created by glaciers. Although the glaciers from the last ice age left over 10,000 years ago, all over New England lies evidence that tells us about being blanketed by thousands of feet of ice. The three geologic curiosities we saw in Weymouth are examples of what can happen under a glacier. To more deeply understand these subglacial features, we can travel to areas of the world where glaciers still exist and study what they leave behind in their wake. This can help us understand the history of these amazing systems and tell us about our own geologic past. The glaciers in this video are from western Svalbard, a set of glacier-covered islands north of Norway. Glaciers around the world are shrinking fast as a result of climate change. So, what can we learn from the clues that glaciers leave behind, and how can that help inform our future? Rocks of all sizes can get moved by glaciers. They can get moved many miles away from their original source. Then, as the glaciers retreat, these rocks get left behind. These rocks, often huge boulders whose rock type does not match the local bedrock, are known as glacial erratics. Scientists can study the rock type, and if they can trace the rock type back to the source, they could use this information to infer the direction that the ice flowed. This is very useful in places where glaciers have long since retreated. Big House Rock in Weymouth is a dramatic example of a glacial erratic. Seeing such a large boulder gives you a sense of the immense power of a glacier. As Big House Rock is, it would be minuscule compared to the 5,000 feet of ice that blanketed this area. So it's not so far-fetched to think that it could have been moved that far. Scientists can also use a technique known as cosmogenic dating, which uses exposure to high-energy particles from outer space to infer when rocks became exposed at the surface. This can help estimate the age at which glaciers covered a particular place. Cosmic rays are produced by events far away in space, like supernovae. When these cosmic rays hit rock, they can alter the atomic nuclei in the rocks. Glaciers absorb these rays and prevent rocks from being affected. But once the rocks are exposed on the surface, their atoms may be changed. The longer they are on the surface, the more of these changes will be observed. By using a cosmogenic dating technique in glacial erratics, geologists led by Christopher Halstead from the University of Vermont were able to reconstruct this detailed history of the retreat of the Laurentide ice sheet at the end of the last ice age. The red indicates the specific location of the edge of the ice sheet as it was retreating. The long snaky hill in Weymouth is known as an esker. In fact, the park in which it sits is appropriately named Great Esker Park. This dramatic hill traces the path of a subglacial stream or river. Although we tend to think just about ice when thinking of glaciers, glaciers contain a significant amount of liquid water, especially in the summer when the air temperature may be above freezing. Also, as a glacier flows, friction between the ice and the bedrock can create meltwater as well. All of this water will flow into a whole system of channels and streams. This image shows a map of the subglacial stream system in the Kronebreen Glacier in Svalbard, Norway. There's quite a lot of water flowing under this glacier. At the front of the glacier face, you can see places where these subglacial streams exit at what are known as upwelling plumes. The color of the water coming off the glacier face gives you an idea of the huge quantity of sediment carried by these streams. At Kongsbreen Glacier, which has recently retreated onto land, you can see the outflow of a subglacial stream. This gives you a sense of how much water and sediment can be flowing under glaciers. Under the stream, sediment will build up, particularly the larger pieces of rock. Then, when the glacier melts, this pile of sediment will be left behind as an echo of the subglacial stream, showing where its meandering path once traveled. As we look from above at the Great Esker in Weymouth, you can imagine the flow of the large stream that flowed under the ice sheet which covered the Boston area thousands of years ago. Another dramatic esker can be found up in western Maine in a place called Five Keysars Ponds near Waterford. Because this esker cuts through the pond so neatly, it's quite clear where the esker is. At the mouth of this esker, you can see the classic U shaped valley. So, in addition to imagining the flow of the water under the glacier, you can imagine where this part of the glacier sat within this valley. What about our nicely rounded hill on top of which sits Great Hill Park in Weymouth? This hill turns out to be a drumlin, which is another subglacial feature commonly seen here in New England. One way drumlins can form is when there is some sort of snag or sticky spot in the bedrock. As the glacier flows, full of sediment, this sediment can build up at these snags. Given enough time, this mound of sediment can be quite large. When the glacier retreats, these mounds are left behind as the hills we call drumlins. Generally, drumlins have one side that is steeper than the other. The steeper side is usually on the side from which the glacier is advancing. Studying drumlins can help geologists reconstruct the position and flow of ancient glaciers. Drumlins are quite common in New England, but because our landscape is so densely covered with forests, towns, and roads, they're not always so easy to pick out. But looking north from the Great Hill Park drumlin, we see the islands of Boston Harbor, and there the classic drumlin shapes are obvious. In fact, noticing that most of these hills have their steeper side on the northwest side of the harbor shows us that the glaciers blanketing the Boston area during the last ice age indeed flowed from the northwest to the southeast into the Atlantic Ocean. In a region like the Arctic, it's relatively easy to study glacial features because of the large number of glaciers still around and the fact that there is very little growing on the land to obscure these features. But as we've seen in a region like New England, which lost its glaciers over 10,000 years ago, and which is now covered with dense forests, farmland, towns, and cities, this is much more difficult. Fortunately, with the use of LiDAR technology, we can get high quality images of what the land surface would look like if we were to take away all of the trees, other plants, and human structures. LiDAR uses planes equipped with lasers to accomplish this. A high resolution LiDAR map of the Weymouth area clearly shows Great Esker Park. It shows in high relief the path that this part of the subglacial river must have taken. The drumlin at Great Hill Park is also clearly visible, as are the many other drumlins in the area, including the Boston Harbor Islands. The LiDAR map of Maine shows the esker that cuts through Five Keysars Ponds near Waterford, Maine. Studying the clues left behind by retreating glaciers can be an exciting detective story. It's fascinating to discover the way these immense, beautiful, and destructive giants moved across the landscape and shaped many of the places we live in today. We've learned that the three geologic features in Weymouth that started our investigation are all the product of loose material being moved and deposited under glaciers. Glacial erratics tell the story of single rocks being moved along a glacier. Eskers chronicle the history of hidden winding rivers moving under glaciers, depositing glacial till as they flow. And the drumlins tell a tale of sediment piling up as glaciers encounter unexpected resistance. But learning about subglacial features is much more than just scientific curiosity. Learning about how these incredible forces of nature work can help us understand and prepare for changes that will inevitably occur as human caused climate change shrinks glaciers further.